What we're going to look at in Chapter 1 is a series of questions related to how we deal with matter. Along with these will be problem-oriented questions. So things like, if we've got a sample, how do I know what the average atomic mass of it is if I know about all the different types of isotopes that make it up? In addition, that we'll mostly be working with the mole specifically, so we'll do a series of examples where we look at how we use the concept of the mole and the periodic table to help us find either how many atoms we have, or maybe how massive a sample should be based on the number of atoms we have. So, to start with this example, first, I've got to set this to a pointer pin. Okay, there we go. So we've got a naturally occurring chlorine sample. It's going to consist of 75.77% chlorine-35 and 24.23% chlorine-37. We want to calculate the average atomic mass for chlorine, or chlorine's atomic mass. So that's the average of all its naturally occurring setups. So what I'm going to do is I'm going to take each together, and it's going to work like a weighted average. So in this case, we have 75.77%. So that would be written as 0.7757. And we're going to multiply that times the mass of the chlorine-35 atom, which is going to be 34.97 AMUs. So we do this first. And to this, we're going to add, I now have 24.23%. So written as a decimal, that's 0.2423. And we're going to multiply it times the mass of a chlorine-37 atom now, which is 36.97 AMUs. When we put this into our calculator, for this here, we're going to get a total of 26.50 AMUs. And here, we're going to get a total of 8.958 AMUs. Note that in each case, I wrote 4 significant figures since I have 4 in my question. We're then going to add these together. And since we're adding, we're looking at decimal places, and our hundredths place is the one we know the least well, because we've got our total on the left is in the hundredths, our total on the right is in the thousandths. So when I add these together, I'm going to get that the atomic mass is 35.45 AMUs. Note that this is a logical answer that we might expect because the majority of our sample is chlorine-35. Therefore, we expect the answer to be closer to chlorine-35, which is 34.97, rather than closer to 36.97, since that's only 24.23% of our sample. It's also a good check to make sure the answer occurs between all of our values. If you had that the atomic mass was something like 32 AMUs or 38 AMUs, that would suggest you did something wrong, since that's suggesting the average is actually higher than the either most heavy atom or lower than the lowest atom. So make sure to do that check to see that you've got a reasonable answer when you do questions like this. If you had had more than 2 compounds, you would or 2 choices in terms of, we only had chlorine-35 and chlorine-37 here, but if you worked with an isotope where there were 3 naturally occurring isotopes, or 4 or 5, all you'd have to do is add each of them together, multiplying by the percentage. None of the process changes other than there's just a few more things to put in. So that's how we deal with natural abundance. Let's now look at the mole, which is where the rest of this section is going to focus on. So how many moles of sodium are there in 45 grams of sodium? So we know that we're going to start with 45.0 grams of sodium. Then I'm going to check my periodic table for the molar mass. Remember that occurs at the bottom, right below the element. So for sodium, we're going to have a mass of 22.99 grams of sodium is going to have a mass of 1 mole of sodium. My grams of sodium will cancel. I'll be left with moles, which is indeed what my problem asks for. And when I do 45 divided by 22.99, I'm going to get 1.96 moles of sodium. Again, 3 significant figures because there were 3 in my question. And make sure to always check on that. And you will note that a lot of questions we tend to have about 3 significant figures. That's just because it's a fairly common amount of how much I'm going to measure carefully, but that doesn't mean it always has to be 3. So make sure you check each time. So now let's go the other way. So that was from grams to moles. Let's do moles to grams. Also, I wrote this here so we can remind you that anytime you see AMU, it is also true that if something has a mass of 6.941 AMUs, it'll also have a molar mass of 6.941 grams per mole. So, there's my pen. We have 2.00 moles of lithium. Now we know we want moles on bottom and we want grams on top. This is because we want to cancel out our moles. So now we'll have our 1 mole on bottom and we'll have our 6.941 on top. The moles will cancel. We then put in our calculator 2 times 6.941. And when we get this, we're going to get 13.9 grams of lithium. So as you can see, we can go both directions. We can go between grams and moles, or moles and grams. So now let's look at one other thing where we, instead of going between moles and grams, we're going to go through between moles and what the number actually stands for, or what the number stands for in mole. So we're not always going to have grams when we're dealing with this, although we will commonly when we're doing this. Although you may have noted, if you started to look at the chapter 2 material, when we get to light, you'll start dealing with it when we're dealing with things like photons, and you don't have grams for that. So it's still possible to use the mole in other contexts. It's not just for mass, although we're going to use grams per mole the most commonly at the beginning. So the world has an estimated 7.5 times 10 to the 18th sand grains. So if we take all the sand grains on Earth, we get about this many. The question is, we want to look at how this compares to the size of the mole. So how many moles of sand grains would this be? So I'm going to divide by 6.022 times 10 to the 23rd, and I'm just going to write grains. That'll be easier. It'll fit on here. And for this, there'll be 1 mole of sand if we do this. So we're going to cancel out our sand grains. And what you'll get, if you put this in your calculator, is that you actually have 1.25 times 10 to the minus 5 moles of sand grains. This is something to keep in mind. We say that the mole is a really big number, but that can be hard to comprehend, as lots of numbers are really big. If I say the number 1 billion, that sounds really big. If I say a trillion, that sounds bigger. If I talk about something like the national debt, that's got a lot of zeros. But when I talk about the mole, I'm talking about a much larger number. And this is a good way to look at that, is if you took every sand grain on Earth, I would not be able to get enough sand grains to make a single mole of sand grains. So when we say we have a mole of atoms, individually this is a very, very large number. And why we've created the unit. Because we don't want to have to deal with trying to talk about numbers like, I've got 2.53 times 10 to the 23rd atoms of helium. That becomes unreasonable. So we use the mole so that we're working in a more reasonable frame to be able to talk about these numbers and compare them to each other. So let's look at another example. So here we have a question of which sample would contain the most atoms. So I'll point out there are 2 ways you can solve this question. One is if you go from grams to moles, and this were a multiple choice, every single conversion from moles to atoms is going to give you the same thing because you're multiplying all of them by 6.022 times 10 to the 23rd. So when we have something in moles, that's a way of telling you how many atoms in this case there are, or later molecules when we're talking about something where we've got more atoms combined together. The only time you really have to go all the way to giving an exact number and using that 6.022 times 10 to the 23rd is when you're explicitly asked, like, here's a number, how many atoms is this exactly, not just in moles. So a lot of times we'll do something like this, where I take my 62 grams, and I know there are 12.011 grams of carbon for 1 mole of carbon. And when I do this, I'm going to get that there are 5.16 moles. And what I'll show you here is that we can indeed go further if we want. And we can go from 1 mole is 6.022 times 10 to the 23rd atoms. I'm going to put that in my calculator, 5.16 times 6.022 times 10 to the 23rd. And when I do that, I'm going to get 3.11 times 10 to the 24th atoms. So if you want to go all that way, you can. But we can actually go through and do this for each one with just going to moles, and we'll be able to tell you which of these has the most atoms. So I've got 224 grams of iron. I know that there are going to be 55 point... Oh, right, I was looking at my paper, but it's actually written up here as well. 55.845 grams of iron for every 1 mole of iron. Here our grams are going to cancel, so we'll be left with moles. And we're going to get that there are 4.01 moles of iron. So that means that currently my carbon has the most atoms, iron's going to have fewer. And if you go through and you take your 4.01 and you multiply it by 6.022 times 10 to the 23rd, you'll find that you would get 2.41 times 10 to the 24th atoms, which is indeed less than our carbon. So I'm just going to keep going to moles for the next 2, though. You can continue to atoms if it's something you want to practice. So let's look at our helium. I did not mean to bring up the menu. So we have 24.0 grams of helium. And we know that for every 4.003 grams of helium, there'll be 1 mole of helium. When I do this, I'm going to get that there are 6.00 moles of helium. And then finally, so that's our most now, because 6 moles is more than 5.16. So we can check our 3 grams of hydrogen. Note that if you were doing this on a test and it's multiple choice, I'm not looking at your work for that part, so it's just getting the correct answer. You could quickly look and go, okay, 3 grams of hydrogen, it has a molar mass around 1, 3 moles is definitely less than 6. But to show the work, if I take my 1.008 grams for 1 mole of hydrogen, I will get that there are 2.98 moles of hydrogen, which indeed is less than 6. So for our sample, we're going to get that C is going to contain the most atoms. So this is the idea when you see a question like this, we have to convert everything into something we can compare based on the question. Because simply looking at grams, you would think the answer B was correct because iron was the heaviest. But we have taken into account that each of these weighs a different amount. But once I get into counting, then those numbers become comparable. So far, we've been doing counting with stuff, but let's try going the other way. Let's try using the idea of calculating a molar mass to figure out what something is, rather than knowing what something is and then calculating either a mass or moles. So anytime I want to know something like the identity of something, in this case, I'm going to want to know the molar mass. Remember, our molar mass is just equal to the mass, generally in grams to make it in the unit we want, over the number in moles. Note that for this problem, we're saying that it is specifically an element. So once I find my molar mass, I'll be able to look at my periodic table and figure out what element it would be. If you did not know it was an element, you might need some more information, since 2 things could have the same molar mass if you combine them in different ways. But once you get down to it being an element, there's only one choice because of the periodic table will limit what your options are. So for this, we need our mass in grams, which the problem has already given us, and our number of atoms in moles. And currently we have it in atoms. So let's convert that. So we have 8.28 times 10 to the 23rd atoms. And now I'm going to convert it. I know that for every 6.022 times 10 to the 23rd atoms, I'm going to get 1 mole. My atoms would cancel and I'm left with moles. And from there, I'm going to get that this sample contains 1.37 moles. Now I can plug both these numbers in here. My sample has 5.50 grams, and I've got 1.37 moles of the sample. When I do that, I'm going to get the molar mass is 4.01 grams per mole. As a reminder, you're not done with your question if you stop here, so make sure that you actually finish the problem, which is to identify the element. You can go to your periodic table, and as your atomic number increases, the mass increases, so you can look until you find something close to here. So if you're too small, you keep moving towards the right or moving down. And if you're too big, you keep moving left and up. So in this case, I go to look, and 4 is kind of a small number, so it's near the top of the periodic table. In this case, I find that helium has a molar mass of 4.0026 grams per mole. That's my closest element, so I'm going to say that this is going to be helium. So we have helium is the identity of the element in this particular sample. Note that we've also told you that it is just one element. Obviously, you could have a sample with multiple things mixed together, and then we would have to do some more work to figure out what it would be based on the molar mass of the sample overall. So that'll conclude the Chapter 1 problems. Hopefully that helps out some. Make sure that you particularly put emphasis on how do we use this molar mass thing to get between mass and number, because we will use that throughout the semester, since many times it is easier to measure the mass of something, such as on a scale, but when we want to do a chemical reaction, we want to know how many atoms there are, or how many molecules of a compound there are. That way we can do our chemical reaction, since our chemical reactions don't have a mass number in them, but instead a number in them. So that's the reason why we're putting so much time into working through these.